You know that feeling when you're just absolutely convinced you're right about something
Oh, yeah.
and you really want to show someone else, like prove it beyond any doubt that it's not just a guess or, your opinion, but something that has to be true.
Mhm.
Maybe you're trying to prove your strategy for a game always works, or I don't know, argue a point so tightly they just can't find any holes in it.
Right. Moving beyond just thinking it's true.
Exactly. How do we get from that strong feeling, or maybe a few examples that worked out, to real, solid, undeniable certainty?
Well, that's a great lead into what we're diving into today.
So today we are taking that deep dive, looking right into that search for certainty, but specifically in the world of mathematics.
Hmm.
We're exploring mathematical demonstrations. You probably know them as proofs.
Right. Proofs. That's the common term.
And these aren't just, abstract exercises for mathematicians locked away somewhere. They're really the foundation, the bedrock that all of mathematics is built on.
Absolutely. They're how mathematical truth gets established with a kind of rigor you don't often find elsewhere.
And our guide for this journey is a set of notes, really insightful notes, that break down what proofs are all about.
Yeah, they lay out the basics, what a proof is, what you need to build one.
And they even get into some specific methods, different techniques mathematicians use to make their critics, so to speak.
It's like getting the blueprint for mathematical certainty.
Okay, so what's our goal here? What are we trying to get out of these notes?
Well, our mission really is to unpack all of that. We want to get a solid grip on the main idea behind a proof. What makes it different from just, showing something seems to work most of the time.
Okay.
We'll dig into the different techniques the source talks about, see the strategies they use for different kinds of problems.
And why does it matter?
And crucially, yeah, why does this superstructured, logical way of thinking matter?
Yeah.
Not just in math, but maybe how it helps us think critically about arguments anywhere.
Sounds good. So we'll start right at the definition, the key parts, and then really spend time on the different types of proofs the notes highlight. We'll use the examples they give to make it all hopefully a bit more concrete.
Yeah, make it less abstract.
It's going to be a journey into, well, logical certainty.
All right, let's get into it. Let's unpack this.
Okay, so first things first. What is a mathematical demonstration or proof according to our source?
Yeah, the definition.
It's defined very simply, actually, but it's powerful. It's a series of logical steps to prove an argument.
A series of logical steps. Okay, that sounds simple, but I bet there's a lot packed into that.
There really is. It's what makes a proof different. It's not just saying, I think this is true, or look, it worked a few times. It's about building this unbreakable chain of reasoning.
Right. I sometimes think of it like building a watertight case in court.
Interesting analogy.
But the only evidence you can use is stuff that's already proven true, like established facts or theorems.
Okay, yeah. And the only method allowed is just pure airtight logic. No loopholes, no maybes, no probablys. It has to be absolutely certain.
That's a really good way to put it. The core function, just like the source says, is to prove a mathematical argument or hypothesis using logic.
Hypothesis. So that's the starting point, the thing you think might be true.
Exactly. You start with your hypothesis, your educated guess, and you put it through this rigorous logical ringer.
Okay.
And here's something really important the source points out. Once that hypothesis survives, once it's been proven, step by logical step, it graduates, it gets promoted, it becomes a theorem.
A theorem. Okay, that sounds important.
It's huge in math because a theorem isn't just something we think is true anymore. It's accepted as a solid, undeniable fact.
Ah.
And the really powerful part is you can then use that theorem, that proven fact, as a building block in future proofs to prove other things.
So you don't have to reinvent the wheel every single time.
Precisely. You build on what came before. The whole structure of math is built like that, layer upon layer of these proven theorems.
That makes a lot of sense. So if you're going to build one of these proofs, what do you actually need? What are the essential ingredients, the rules of the game? The notes lay out some key elements, right?
Yes, they do. First up, it mentions using facts or theorems that are already known to be true.
Right, the building blocks we just talked about.
Exactly. Your starting points, the justifications for your steps, they have to be grounded in things we've already established as true axioms, definitions, previously proven theorems.
You're not just making things up as you go along.
Definitely not. Then, the source really stresses that it follows a logical sequence of steps.
The chain of logic idea again.
It's not just a random collection of true statements.
Yeah.
Each step has to flow, like directly and logically from the one before it, or from those established facts you started with.
No jumps, no hidden assumptions.
None that aren't justified. If there's a gap, the proof fails. A single illogical step breaks the whole chain.
Okay, that's strict.
It has to be. The notes also say a good proof needs to show the reasoning used to reach the conclusion.
So you have to show your work, basically.
Exactly, but on a deep logical level.
Right.
You can't just state the beginning and the end. You have to lay out the whole path, step by logical step, showing how you got from A to B.
Making it totally transparent so anyone can check your logic.
That's a perfect way to put it.
Yeah.
It's not magic, it's a transparent argument. And finally, the source says you need to end your demonstration with a statement.
The conclusion, like QED.
Sort of, yeah. It's the formal sign-off, a clear declaration that you've proven what you set out to prove. The hypothesis is now confirmed. It's a theorem.
Okay, dotting the I's and crossing the T's. Got it.
It signals, we're done. Argument successful.
Right.
So just to quickly sum up that core idea from the source, a proof is this structured logical argument. It uses established facts and theorems, follows a strict logical sequence, shows all its reasoning, and aims to prove, definitively, that a statement must be true under the given conditions. Not just that it seems true sometimes.
Okay, that gives us a really solid picture of what a proof is. But, practically, how do you actually go about building one? Do the notes give us steps for that?
They do, yeah. A kind of general blueprint for construction. Step 1, really important for clarity. Write down any information that is being used.
Your starting materials, your given.
Exactly. What are the conditions? What facts are you assuming or starting with? You have to be crystal clear about that foundation.
So if you're proving something about, I don't know, triangles, you'd write down what a triangle is, maybe properties of angle.
Precisely. The relevant definitions and known facts for this specific problem. Then, step 2. Make sure each step follows a logical sequence.
We talked about this as an element, but here it's an action step.
Right. As you're building the proof, statement by statement, you have to actively check, does this really follow logically from what I just established? Is the reasoning sound? No gaps allowed.
That's the real work, connecting the dots logically.
It is. And step 3 is to use facts and theorems. As you move through your logical chain, you bring in those established truths.
The library of known math facts.
Exactly. You might say, okay, we know X is true from Theorem 7, and we started with Y, so therefore Z must follow. You use the existing knowledge to justify your moves.
It really shows how math builds on itself.
It absolutely does.
Mm-hmm.
You don't need to prove basic arithmetic every time you use it in a proof. And step 4, reinforcing what we said earlier, is end your demonstration with a statement.
Plant the flag. Declare victory.
Basically, yes. A clear signal. Proof complete, hypothesis proven.
Okay. The source mentioned an example theorem, didn't it? Something about even numbers.
It did. An even number squared gives an even number. The notes don't give the full proof, but we can quickly sketch how the steps would apply, conceptually.
Yeah, let's do that.
Okay, so step 1, write down givens. You'd write the definition. An even number n is an integer that can be written as 2 times some integer k. So n is 2k.
Got it. N equals 2k.
Step 2 and 3, logical sequence using facts. Your hypothesis is if n is even, then n squared is even. So you look at n squared, that's 2k squared.
Okay,
Now use a known algebraic fact. 2k2 equals 4k2.
Right.
Can we show it? That is even, well, use another fact. 4k2 can be rewritten as 2 times 2k2.
Ah, factoring out the 2.
Exactly. And since k is an integer, k squared is an integer, and 2 times k squared is also an integer, let's call it m. So 2k2 is an integer, where m is an integer.
Okay.
So we've shown that n squared equals 2 times m, where m is an integer. And what's the definition of an even number?
It's 2 times an integer, so n squared fits the definition. It's even.
Precisely. You followed a logical sequence, used established facts like algebra rules and properties of integers, and reached the conclusion.
And then step 4, conclude clearly.
You'd write something like, therefore, the square of any even number is even. And boom, once proven, that's a theorem you can use elsewhere.
Okay, walking through that, even without all the formal notation, makes the process feel much more tangible.
Good. That's the idea. It's a structured journey.
All right, so we got the general idea and the steps. Now, the notes get into specific types of proofs, right? Different strategies.
Yeah, different tools for different jobs, essentially, depending on what kind of statement you're trying to prove or maybe disprove. The first one listed is demonstration by deduction.
Deduction. What does that mean in this context? The source says something about testing logic using possible outcomes.
Yeah, it's about reasoning from general principles or premises to specific conclusions. Or, like the example in the notes shows, it's about testing a conditional statement, an if A, then B statement by looking very carefully at all the ways A can be true.
So, if this part is true, then does this other part automatically have to be true? And deduction checks that link.
Exactly. It explores the logical consequences. The source uses that non-mathematical weekend example, which is actually quite helpful here.
Right, the weekend one. Argument A is, yes, today is the weekend.
Okay. And if that statement is true, if today is the weekend, what are the actual possibilities? The source points out there are only two.
It's either Saturday or it's Sunday. Those are the only ways today is the weekend can be true.
Right. Those are the possible answers or outcomes for argument A.
Then the second part, argument B, is, so tomorrow will be a weekday?
And the overall argument they're testing with deduction is the conditional statement. If today's the weekend, then tomorrow will be a weekday B.
Okay, so how does deduction test that?
It looks at each of those ways. A can be true, Saturday, Sunday, and checks if B, tomorrow's a weekday, holds true in both scenarios.
All right, so case one from the source. If today's Saturday.
Then tomorrow is Sunday. Now we check the conditional statement for this case. Is the premise, today is the weekend, true? Yes, it's Saturday. Is the conclusion tomorrow will be a weekday true?
No, tomorrow's Sunday, which is still the weekend.
Exactly. So in this specific case, Saturday, the premise A is true, but the conclusion B is false. The source says this makes the whole argument, the if A, then B, statement false in this case.
Because the then part didn't follow from the if part here.
Precisely. For an if A, then B statement to be logically true overall, B must be true every single time A is true. Finding just one instance where A is true and B is false breaks the whole thing.
Okay, so what about the other case? The source says, on the other hand, if it were Sunday.
Right. Case 2. Today is Sunday. Is the premise today is the weekend true? Yes. What about the conclusion tomorrow will be a weekday?
Tomorrow's Monday, and yes, Monday is a weekday.
So in this case, Sunday, the premise A is true, and the conclusion B is also true. The conditional statement holds up here.
But that doesn't save the overall argument, right? Because it already failed for Saturday.
Exactly right. Because the conditional statement, if today's the weekend, then tomorrow will be a weekday, did not hold true in all possible scenarios where the premise was met. It failed on Saturday. The deduction shows the overall statement is false. The conclusion doesn't necessarily follow from the premise in all instances.
So the source concluding, this makes the argument false, refers to the entire if weekend, then weekday statement.
Yes. The deduction involved examining the premise's possibilities and testing the consequence. It's a systematic check.
That example really clarifies how deduction works by breaking things down. It feels like something we do informally all the time, but this makes it rigorous.
It is. It's about making sure the logical connections hold up under scrutiny across all relevant scenarios.
Okay, so deduction tests if something must be true. What about when you want to show something is definitely not true? The next method sounds perfect for that. Proof by counterexample.
Yes, the elegant disproof. This one's especially useful when you're up against a statement claiming something's always true, or true for all things in a certain category.
Like, all swans are white.
Exactly. And how do you disprove that? You don't need to check every swan.
You just need to find one black swan.
Precisely. That one black swan is your counterexample. As the source puts it, you just need a single example that does not prove the hypothesis that it is false. Finding one instance where the claim fails is enough to show the claim itself is false.
It seems so efficient. If someone says something is always the case, find just one time it isn't and you've won the argument, logically speaking.
It's the definitive way to debunk a universal claim. If there's even one exception, the always part is broken. The source gives us a mathematical example here.
Okay, what's the claim we're trying to disprove?
The hypothesis is, the sum of the square of two integers is always a number that is the result of squaring another integer.
Whoa, okay, let's unpack that. Take any integer, square it. Take another integer, square it. Add those results together. The claim is that the sum you get will always be a perfect square itself, the result of squaring some other integer.
Right. Integer squared plus integer squared equals integer squared. Always. And that always is what we're targeting.
So to disprove this with a counterexample, we need to find just one pair of integers.
Where you square them, add the squares.
And the result is not a perfect square.
Exactly. The source suggests trying the numbers 4 and 9.
Okay, let's check. Are 4 and 9 themselves the squares of integers?
Yes, 4 is 2 squared and 9 is 3 squared. So they fit the first part, they are squares of integers.
Good. Now, according to the hypothesis, their sum should also be a perfect square. What's the sum? 4 plus 9, that's 13.
Okay, 13. Now the crucial question, is 13 a perfect square? Is there any integer you can multiply by itself to get 13?
No. 3 times 3 is 9, 4 times 4 is 16, 13's in between. It's not a perfect square.
Correct. The source even lists some perfect squares between 1 and 81, 4, 9, 16, 25, and so on. 13 isn't on that list.
So we found it. We found a pair of numbers, 4 and 9, which are perfect squares, but their sum, 13, is not a perfect square.
That single instance, 4 plus 9, is our counterexample.
It directly contradicts the claim that the sum is always a perfect square.
Exactly. Because we found this one case where it fails. The original hypothesis is proven false. As the source says, this means that the hypothesis we started from is not true.
It's quite satisfying finding that one fatal flaw in a universal statement.
It is. It shows the power of a single, well-chosen exception to overturn a broad claim. Very definitive.
Okay, so deduction for checking logic, counterexample for disproving always statements. What if you need to prove something is true and it applies to several different situations or categories? This sounds like the next method, demonstration by cases.
Yes, proof by cases. This is the strategy you use when the problem you're tackling naturally splits into a finite number of distinct scenarios.
Finite being the key word there. It has to be a manageable number of cases.
Generally, yes. The idea, as the source says, is to examine each possible case related to the hypothesis and checking each one separately.
So unlike a counterexample where one failure sinks the ship, here you need success in every single case to prove the statement.
That's exactly it. You identify all the different distinct situations covered by your hypothesis. Then you have to prove that the hypothesis holds true within each of those situations, one by one.
Okay.
If you can successfully show it's true for every single case, and those cases cover all the possibilities, then you've proven the statement universally for the conditions defined.
It sounds very thorough, like you're making sure you cover all the bases.
It is thorough. It's useful when proving it for one case doesn't automatically guarantee it for others. The source gives an example for this one too.
All right, what's the example?
Prove that the sum of two consecutive square integers, whose square is between 1 and 81, is an odd number.
Okay, let's break that down. We need square integers.
Specifically squares that fall between 1 and 81.
Yeah.
The source lists them for us. 4, 9, 16, 25, 36, 49, 64.
Right, those are 2 squared up to 8 squared. So we're working just with that list. 4, 9, 16, 25, 36, 49, 64.
Correct. And the hypothesis is about pairs of consecutive squares from that specific list.
Consecutive means right next to each other in the list.
Yes. So we need to identify all those consecutive pairs. These pairs will be our distinct cases that we need to check.
Okay, let's list them out. The pairs from that list are
Case 1,
4 and 9,
Case 2,
9 and 16,
Case 3,
16 and 25,
Case 4,
25 and 36,
Case 5,
36 and 49,
and Case 6.
49 and 64. That's all of them from the list.
Perfect. Those are our 6 distinct cases. Now, the method requires us to check if the hypothesis holds true for each case. What's the hypothesis again?
That the sum of the pair is an odd number.
Right. So we check each case. The source explicitly does case 1, 4 plus 9 is 13. Is 13 odd?
Yes, 13 is odd. So check for case 1.
Now, interestingly, the source doesn't then show the calculations for cases 2 through 6.
Ooh, it doesn't show 9 plus 16, 16 plus 25, etc.
No, but it makes a concluding statement about them.
Yeah.
It says, it can be seen that all the numbers added together result in an odd number.
Ah, okay. So it's telling us that if we were to do the sums for all the other pairs, 9 plus 16, 25, 16 plus 25, 41, 25 plus 36, 61, 36 plus 49, 85, 49 plus 64, 113, they would all turn out to be odd numbers.
Exactly. It asserts that the check holds for all the identified cases.
So because the claim, the sum is odd, is true for case 1, and the source assures us it's true for cases 2, 3, 4, 5, and 6 as well.
Meaning it's true in every single possible case covered by the premise, consecutive squares from that list.
Then the overall statement is proven true by this method of checking all the cases.
That's proof by cases. You break it down, prove each part, and if all parts hold, the whole thing holds. It's about exhaustive verification within defined boundaries.
Makes sense. Managing complexity by dividing and conquering. All right, that leaves one more type from the notes. Proof by contradiction. This is the one that always feels a bit backward.
Yeah, it can feel counterintuitive at first. Reductio ad absurdum.
Reduction to absurdity. Sounds dramatic. So you want to prove something is true by starting off assuming it's false.
That's exactly the starting move. It's a very powerful technique, especially when a direct proof is hard to find.
So if I want to prove statement X is true, I literally start my proof by writing assume statement X is false.
Pretty much, yes. You temporarily take the opposite of what you want to prove and treat it as a true premise, just for the sake of argument.
Okay, then what?
Then you use totally valid logic, established facts, theorems, just like in any other proof to see where that assumption leads you. You deduce the consequences of assuming the opposite.
And the goal is to show that this path leads somewhere impossible, like a dead end.
Exactly. You aim to derive something that is demonstrably false. Either it contradicts a known mathematical fact, like 2 + 2 = 5, or it contradicts something else you've already logically established, maybe even your initial assumption itself. That's the contradiction.
Ah, okay. So the logic goes, if we assume X is false, then step. Oh, wait, that means something impossible must be true, but impossible things can't be true.
Therefore, our starting assumption, that X was false, must have been wrong in the first place.
And if the assumption X is false is wrong,
Then the only remaining possibility is that X is true, which is what you wanted to prove all along.
wow. It's like proving yourself right by showing that being wrong leads to nonsense.
That's a great way to sum it up. You expose the absurdity of the alternative. The source gives a clear mathematical example.
Let's hear it.
Prove that there do not exist two integers a and b, for which it is true that 5a plus 10b = 1.
Okay, the statement is, no integers a, b satisfy 5a plus 10b = 1. So using contradiction, step 1 is assume the opposite.
Right. As the source says, assuming the opposite, we assume that there do exist integers a and b such that 5a plus 10b = 1 is true. That's our starting point.
Okay, assume integers a, b exist where 5a plus 10b = 1. Now we explore the consequences.
The source points out something crucial about integers. If they are integers, then the result of a plus 2b must also be whole. Why is that true?
Let's see. If b is an integer, then 2 times b is also an integer. And if a is an integer and 2b is an integer, then adding them, a plus 2b, must also result in an integer, because integers are closed under multiplication and addition, right?
Perfect. That closure property is key. So if our assumption holds, such integers a, b exist, then it must be true that the expression a plus 2b represents some integer. Let's keep that in mind.
Okay, a plus 2b is an integer. Now back to the equation. 5a plus 10b = 1.
Can we simplify that left side? Notice anything?
Both terms have a 5 in them. We can factor out 5. So 5 times a plus 2b = 1.
Exactly. 5a plus 2b = 1. Now combine this with what we just figured out.
But we figured out that a plus 2b has to be a whole number in integer.
So the equation becomes 5 multiplied by some integer = 1.
5 times an integer = 1. Wait, can that happen? The multiples of 5 are like 0, 5, 10, none is 5, ness is 10. 1 isn't in that list. You can't multiply 5 by a whole number and get 1.
Correct. Or think about it another way. If 5a plus 2b = 1, divide both sides by 5.
Then you get a plus 2b = 15.
But what did we establish about a plus 2b?
We said it had to be an integer. And 15 is, well, it's not an integer. It's a fraction.
And that is the contradiction. Our initial assumption that integers a and b exist satisfying the equation has logically led us to an impossible situation. Something that must be an integer, a plus 2b, must also be equal to something that is definitely not an integer, 15.
An integer cannot equal 15. That's absurd.
Exactly. It's the absurdity we were looking for. The source says, therefore we have a contradiction which makes our statement false. Which statement is false?
The one we started with the assumption that such integers do exist? That assumption led to nonsense, so the assumption must be wrong.
Precisely. And if the assumption such integers exist is false,
Then the original statement, no such integers exist, must be true.
and that's the proof by contradiction complete. The source confirms. Since the opposite has been proven false, then the original statement is true.
That is really clever. It's like boxing the problem in by showing the alternative is impossible.
It's a very powerful tool in the mathematician's kit, especially for non-existence proofs like that one.
Okay, so we've explored these 4 key methods from the notes. Deduction, testing logic via outcomes, counterexample, one failure disproves always, cases, proving by checking all scenarios, and contradiction, proving by showing the opposite is absurd.
And the notes add one more general point about proofs, especially those claiming something about all integers.
Oh yeah, what's that?
It says, if the proof applies to any integer, and a proof only works for even numbers, it must be demonstrated that it also works for odd numbers, so that it is valid for all integers.
Ah, that makes sense. It connects back to the idea of covering all the bases, like in proof by cases. If you claim something for all integers, you can't just prove it for half of them, the even ones.
Exactly. You need to either show it works for the odds separately, or your proof method needs to inherently cover both even and odd situations right from the start.
Your proof has to match the scope of your claim. If you claim all, you got to prove all.
Precisely. The rigor demands completeness for the domain you're claiming.
Which brings us to the really big question, maybe the most important one for our listeners. Why does all this matter? Why should someone who isn't a mathematician care about deduction, counterexamples, or contradiction?
That's the crucial connection, isn't it?
Yeah.
Because these methods, even though we've seen them applied to numbers and equations here, they're really about fundamental structures of sound reasoning.
They're like models for thinking clearly.
Exactly. The skills involve building a logical argument, step by step, checking every link, testing claims rigorously, looking for exceptions, breaking problems down, spotting when assumptions lead to nonsense. These aren't just math skills. They are critical thinking skills.
Applicable everywhere.
Absolutely. Think about everyday life. You read an article, you hear a political argument, you see an advertisement making a claim.
Yeah, you're constantly bombarded with arguments and claims.
Right. Do you just accept them? Or do you maybe instinctively apply some of this mathematical style scrutiny?
Like if you hear a really broad statement, this new policy will benefit everyone.
Understanding proof by counterexample might make you immediately think, okay, everyone, is there anyone it won't benefit? Can I think of just one case where this fails? Finding that one counterexample changes the whole evaluation of the claim.
Or if someone argues, if we do X, then Y is guaranteed to happen.
Knowing about deduction and proof by cases encourages you to ask, okay, let's assume we do X. What are the different ways X could play out? Does Y really follow in all of those scenarios? Or just some? Are there situations where X happens, but Y doesn't?
You're testing the logical link, just like in the weekend example.
Exactly. And that proof by contradiction idea. When an argument just feels off, even if you can't immediately say why,
Yeah.
you might mentally play it out. Okay, let's pretend for a second this argument is wrong.
Mm.
What would the consequences be? Does that lead to something ridiculous or something that contradicts other things I know are true? If it does, it suggests the original argument might actually be stronger than it first appeared, or vice versa.
So these aren't just math tricks. They're like refined tools for analyzing information and arguments in any context.
Precisely. In a world that's just full of information and often conflicting information, where certainty feels hard to come by, mathematical proof stands as this amazing example of how we can achieve certainty through careful, structured, logical reasoning.
It's a gold standard for thinking.
It provides a framework. Demand evidence, check the logic, explore the possibilities systematically.
All right, so let's wrap up this deep dive. We've looked at what a mathematical demonstration, a proof, really is, that logical journey from a hypothesis to a proven theorem, built on solid facts and clear steps. And we explored 4 key strategies from our source material for making that journey, or for showing a claim is false: the careful testing of deduction,
The swift kill of a counterexample,
the thorough coverage of proof by cases.
and that clever twist of proof by contradiction.
And we've seen through the examples how these aren't just abstract concepts, but practical tools for establishing truth.
Tools whose underlying principles of structured reasoning are incredibly valuable, far beyond just math.
So maybe the takeaway for you listening is this. The next time you encounter a strong claim or a complex argument, or you just really need to be sure about something,
Whether it's work or data or just figuring something out.
try thinking like a mathematician for a moment. Ask those questions. Can I find a counterexample? Does the logic hold up in all the important cases? If I assume the opposite, does it lead somewhere impossible?
That ability to demonstrate truth or expose falsehood using clear, verifiable logic. It's a genuinely powerful skill to cultivate. Understanding proofs helps illuminate just how powerful.
Absolutely. Well, that's been our deep dive into the world of mathematical demonstrations. We really hope you found some useful nuggets in there to think about, maybe some tools for your own critical thinking toolkit.